All right, continuing with chapter 4, we're getting into section 3, which is giving us more applications of the derivative. More specifically, this is going to be derivatives that we would use if we were going to sketch a curve, but more specifically even than that, is it's going to be using derivatives to tell us information about a function. Where maximums and minimums occur, where the function will be concave up and concave down, where concavity changes, where a function's increasing and decreasing, things like that. These are very, very powerful tools for us to know about how a function's behaving. All right, in the past, one of the important uses of derivatives was as an aid in curve sketching, to actually be able to see the graph. Even though we usually use a calculator or a computer nowadays to draw complicated graphs, it's still important to understand the relationship between derivatives and graphs and what those derivatives tell us about the graphs. For example, the first derivative, if we know that y prime is positive, we know that the curve is rising. We know that y is increasing. Y prime positive, y increasing. If y prime is negative, then we know that the curve is falling, or y is decreasing. If we know that y prime is 0, then we have a possible local maximum or minimum. And the same thing there is if it's undefined, we have a possible local maximum or minimum. All right, and if we look at the second derivative, we take the derivative and then we take it again, then if y double prime is positive, the function is going to be concave up, like this. What that means is the rate of change of the slope is positive, so the slope is increasing. The slope is increasing, not necessarily y is increasing. Y prime would be increasing if y double prime is positive, but not necessarily y. Notice here, y is going down, but the slope is very negative, less negative, even less negative, 0, positive, positive, more positive, more positive. So y double prime tells us how the slope of the function is changing. So if y double prime is negative, the curve is going to be concave down. The slope is going to be decreasing over that interval, like this. And if y double prime is 0, that means we have a possible inflection point. That is where the concavity changes. Here it's concave down, here it's concave up. This is a point of inflection. Now, just like we talked about possible local maximum and minimum, it's a possible inflection point. This is not enough to prove that's an inflection point. This is not enough to prove that we have a local maximum or minimum. Remember that. Just the derivative being 0 or the second derivative being 0 is not enough. You actually have to prove what it's doing. All right, so what we're going to do is we're going to end up graphing this function right here. But along the way, we're going to do all kinds of neat little things to find out information about the graph and how it's going to behave, so we know where to put points. So we know that there are roots or zeros at x equals -1 and x equals 2, where this thing right here equals 0. That means those are going to be x-intercepts. If we find y prime, we get 3x squared minus 6x. We can factor this, set it equal to 0. And we're going to get x, well, take out a common 3, factor, and we get x equals 0, and x minus 2 equals 0, or x times x minus 2 equals 0, which means we can split that thing up, and x equals 0, and x equals 2. These are places where the derivative equals 0. Once again, think back to what we just wrote down. That means that these two values are possible local maximums and minimums. We don't know yet, but we're about to find out. So we have possible extreme values at 0 and 2. We can use a chart to organize our thoughts. So here's what I'm going to do. I'm going to make a little chart, and I'm going to put 0 here, and I'm going to put 2 here. And what I want is, see, here's the thing. If these are the only values where this derivative is equal to 0, these are the only values where this thing can change from positive to negative. Because what's the only way that on a graph that you can go from a positive value to a negative value if it's continuous? You have to cross the 0. How can you go from negative to positive? You have to cross the 0. So if these are the places, 0 and 2, are the places where the derivative is equal to 0, then these are the only places where the slope can change from negative to positive or positive to negative. So what you want to do, what you can think about is that means that when I plug a value in for the interval here, so this little part right here is going to represent everything 0 all the way back to negative infinity. And if I choose one value in this interval, let's say negative 1, once I find out what the slope is at negative 1, I know the slope for the entire interval, negative infinity to 0. Because 0 is the first place it can change. It can't change anywhere else over here. All right, and the same thing with 0 to 2. I can choose any value that I want in between 0 and 2, and that one value will tell me what the slope is for the, or what the derivative and the slope, same thing, is for the entire interval, because it cannot change from 0 to 2 until it gets to 2. So I'm going to choose a value in there. Let's choose 1. And then the same situation over here. This represents 2 all the way to infinity. Because there's no other place over here where this derivative can be 0, which means there's no other place over there where the slope can change from positive to negative. So if I choose some value larger than 2, let's choose, well, 3, the slope at that value will represent and tell me what the slope is for this entire interval. So we're breaking, this thing actually here, right here is breaking this thing up. It's breaking the number line up into parts. So when I take my negative 1 here, I want to plug it into my derivative right here, but you can also plug it in right here. The reason why, don't ignore the 0 part, but you can plug it in right there because it's already factored. What happens when you get a negative here, negative 1 times negative 1 minus 2? Well, we're going to get a negative times a negative, which gives us a positive. And guys, the only thing I'm worried about here is the sign. I don't care what the number is. The number does not matter, only the sign. Now, just to prove that that's right, let's go back up here and plug it in right here. If we take negative 1 and plug it in right here, what's going to happen? Well, we've got 3 times negative 1 squared, which is 1, minus 6 times negative 1. Well, negative 6 times negative 1 gives me a positive 6. So this is 3 plus 6, which is equal to 9, which of course is positive, which is what I found. So I typically would use that factored part just because I can break it up and it's a little easier calculations, and all I'm worried about is the sign. So when I plug in my 1 right here, I'm going to have a positive here for the x, positive 1, and then 1 minus 2 gives me a negative. When I multiply a positive times a negative, I'm going to get a negative. So what I've just found here is that this function is increasing from negative infinity all the way up to 0, and it's decreasing over the interval from 0 to 2. And then all I have to do is plug in my 3 here to find out what it's doing over there. So if I plug in 3 for x, of course, it's going to be just a plus. And right here, 3 minus 2 is going to give me a positive there. Well, a positive times a positive gives me a positive. And the reason I'm multiplying is because I'm finding this value and that value, and those are multiplied together. So now, it's increasing from negative infinity to 0, decreasing from 0 to 2, and increasing from 2 to infinity. So that's what that table right there tells me. Because this right here is nothing more than the slope, y prime, y prime, or slope, because I'm plugging this into y prime to find what the values are. Now, not only that, but I can look at this, and if this is a critical point, remember that's a possible maximum or minimum, what do I know happens if I go from an increasing function to a decreasing function? Well, if I'm going up on this side and I'm coming down on this side of that point, what do I know that point has to be? Well, it has to be a local max, a local maximum. And over here, if I'm going down before the critical point and then going up after, what do I know? That has to be a local minimum. So now I can identify what my points actually are. I know where they occur. I just have to find out what the value is. So all I would do would be go back up to the original function and plug in my 0. What happens when you get 0 plus 1? You get 1. 0 minus 2, you get negative 2, but you have to square it. So negative 2 squared is 4. So that means we have the point 0, 4, and it's a local maximum, is a local maximum. And then we go back up and do the exact same thing, but we do it with 2. So we get 2 plus 1 gives me 3 there. And then 2 minus 2 gives me 0 there. And then 3 times 0 is going to give me 0. So at 2, 0, that is a local minimum. So we found all that just by analyzing the derivative of this thing and using a chart. Now, once again, let me refresh your memory here. If you're asked to justify maximums and minimums on the AP exam free response questions, this thing right here is not enough. You have to be able to tell them why. So you would say 0, 4 is a local maximum since y prime equals 0 at 0 and y prime changes from positive to negative there. And you could do something similar with local minimum. 2, 0 is a local minimum since y prime equals 0 at x equals 2 and y prime changes from a negative to a positive at that point. That would be enough also. You have to back it up. This chart is not enough information. You've got to tell them what the chart actually tells you. All right, and if you're curious, here are a couple of other written out good justifications for why you can say there's a local maximum at 0, 4 and a local minimum at 2, 0. And once again, on the AP exam, it's not sufficient to draw this chart. And his chart's a little different than mine. He put the 0 and the 2 on the bottom. And these zeros just identify that that's where the derivative is equal to 0. I'm not a big fan of his chart. That's why I showed you mine. All right, now to also find another way that you can use find the maximums and minimums is you could use the second derivative test. Now we haven't talked about this one. The second derivative test simply says that if you take the second derivative and evaluate it at those critical points, it'll tell you whether the thing is concave up or concave down. What that tells you is this. If you've got a critical point right here and your second derivative test tells you the thing is concave up, then what do you know that has to be? It has to be a local minimum. If you've got a critical point here and you do your second derivative test and it tells you that it's concave down, then this has to be a local maximum. So that's what the second derivative test tells you. So that's what we're going to do here is the second derivative test. We're going to plug in 0, we're going to plug in 2, and we're going to verify that what we just found with our chart is correct. So y double prime of 0 gives me 6 times 0 minus 6, which gives me a negative. That means it's concave down at 0, and therefore we would have that first case that I showed you, or the second case, it would be a local maximum. And there will be the justification there if you use the second derivative test to prove a local maximum. All right, and y prime of 2, 6 times 2 gives you 12. 12 minus 6 gives you a positive 6. That means that it would be concave up, and that would be a local minimum. So your justification with that for the second derivative test would be because the second derivative at x equals 2 is positive, the graph is concave up, and therefore 2, 0, the critical point, is a local minimum. So that would be another way using the second derivative test that you could actually prove local maximums and local minimums. The justifications on these are important. They will typically not give you the point for finding the value if you cannot justify for it. And these are the ones where your justifications are your justifications are more involved, are going to be the ones where you do not have a calculator. So you're going to have to be able to find the stuff anyway and justify it. All right, now when we look for inflection points, setting the second derivative equal to 0 and solving. So we've already found the second derivative. It was 6x minus 6. Set that equal to 0, and then you've got a common 6 you can take out, and you get that x equals 1. So x equals 1 is a possible point of inflection. We have to prove or verify that concavity actually changes there. And we can do a chart much like the last one. So we're going to put 1 right here. And notice we're talking about y double prime this time. Choose some value less than 0, some value greater than 2. And when we plug those values in, by the way, we've already put both these values in, so they're ideal values for us to use. What did we find at 0? We found that the second derivative was negative. That means that it's concave down. With 2, we plug it in, and we're going to get positive 6, but all we're worried about is the positive, so that means that it's concave up. When we don't have to determine which way this changes, as long as the sign changes from one side of our possible point of inflection to the other, concavity is going to change. We don't care whether it's positive to negative or negative to positive. So just this amount right here tells us that we do have a point of inflection at x equals 1 because concavity changes. And with this one, the justification, you can just simply say y double prime changes sign. You don't have to say positive to negative or negative to positive, specifically like you do with a maximum and minimum. Guys, if you justify a maximum by saying it changes from negative to positive with a first derivative test, you're not going to get the point. That's an incorrect justification. If your first derivative goes from negative to positive, that's a local minimum. So be careful. There you have to be very specific about how the sign changes. With this one, it doesn't. When you're justifying maximums and minimums, you've got to be very specific about how the signs change. With concavity, you don't. As long as the concavity changes, you're good. All right, so the justification would be there is an inflection point at x equals 1 because the second derivative changes from negative to positive. That's all the justification you need for a point of inflection. All right, now we're going to take all the information that we've put together, plus a couple extra points, and we're going to sketch the graph. Now, guys, let me tell you something. You're not going to have to, well, let me change that, because they have actually done one in the past. Chances are pretty good you're not going to have to do an in-depth graph like this. If they do anything, they'll give you an interval you have to sketch it over, and they'll give you some they'll give you the table that's got a bunch of values, like you're going to be looking at up here. They won't make you do both, or they never have. But you should be able to do both. It's just going to take a lot longer than if they don't give you one or the other. But you should be able to take the information we just found and get a general idea of what this graph's going to do. So let's go ahead and get started. And we're going to plot the points as we go. So we have the point -1, 0. That's just a random point we put on there. It wasn't one of the points we found anything about. And the derivative at that point is 9. And the second derivative is -12. So that means that it is rising, but it's concave down, which means the slope is decreasing. It's going up really steep, but the slope is decreasing. And there's the point we're going to use. Now, the next point we get to is one of our critical points. We found the point 0,4 was a local maximum, which had a derivative of 0 and a second derivative of -6, which means it's concave down there. So right there, by looking at this, we know that our function was an x cubed. So from x cubed, we know it's going to be coming up from the bottom, and it's going to be going up. If you remember your end behavior from pre-cal, that's what we're using here. So the down, up, down, those things, where you're doing on either end, that's what we're looking at. So we're going to come up from this direction. Sorry, we don't want that yet. We're going to be coming up from this direction. We know it's concave down here, so we can almost just sketch in a little down thing there, a little U going down. And then our next point is going to be our critical point, which occurs at 1, 2. We found the 2 by plugging it into the original value. Slope is -3, and the second derivative is 0. It's falling, it's decreasing, and we have an inflection point. There's the point. There's our inflection point right there. All right, our next value is our next maximum and minimum, and it's going to be the minimum, the local minimum that occurred at 2, 0. First derivative of 0, second derivative of 6, which means it's concave up. So we're going to go up right there. Another way that we could identify that is if you look all the way back at the original graph, what do we know about 2? It's a 0 that had a multiple of 2. That means we're going to have a bounce there. All right, and then the last one, we're going to choose some other value over here. We're going to choose a value at 3, and we get 3, 4 as the point, and calculate what the slope is, calculate what the second derivative is, and we end up having a slope of 9, and it is increasing. The slope is increasing because of the second derivative being positive. So that means this thing's getting steeper and steeper the further it goes. All right, and then all we have to do is just draw our graph with our nice smooth curve going through and hitting all our points. And we found absolutely everything we needed to do that with the calculations we did just a second ago. So it's not something that's all that confusing or complex. It just takes some time sometimes. And that is it. Make sure that you know how to use y prime, y double prime to tell things and learn things about what the graph's behavior is. That's the big thing you need to get out of this equation. Now, if you can take those values of y prime and tell what the graph is doing and sketch it, that would be even better. But just make sure you know that y prime is the slope all the time. Y double prime is telling you about how the slope is changing and also its concavity and how you can use the first derivative and the second derivative to find maximum minimums and inflection points where concavity changes.